Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello and thank you for joining us on yet another episode of the podcast we like to affectionately call Space Nuts, episode 132, as against 321, which we're not quite at yet. And joining me,
soon.
joining me, my partner in crime, astronomer at large, Fred Watson.
Hey, hi Andrew.
How are you, Fred?
Yes, all good, thanks.
That's good. Yes, I confused myself there for a moment. Today we're going to be talking about the announcement by NASA that it's locked in partners for its next set of missions to the moon, which is very exciting. They're going back, yes, and they're taking people with them. We also look at the OSIRIS-REx spacecraft. It's reached its destination, which off the top of my head was 101955 Bennu, I think. But Fred will be able to correct me. And a couple of questions. One that's come from Scott about the age of the universe, and another from Kevin about starlight being the same from all stars, regardless of what kind of stars they are. And he wondered why. And that is a very good question, Kevin. We'll get to all of that very soon. But first, NASA has basically said these people are going to help us get to the moon and back. Well, maybe they won't come back. But anyway, we'll find out. What's going on here, Fred?
Well, it's really an announcement by NASA about the US companies that are going to help NASA get to the moon, basically. So this is, it's a fairly preliminary fanfare, but it is interesting. The companies that have been chosen, and they include some big names like Lockheed Martin and other companies like that, as well as some smaller and very interesting sounding companies. They are going to contract to NASA to develop technologies. It's really all about the preparatory work that will go into exploring the moon a bit better, actually. So there'll be landers that will essentially go and basically explore the chemical makeup of the moon in much greater detail than we already know, and other technologies to allow the future lunar missions to take place. So the reason why this is different from stuff that's happened before, Andrew, is that NASA will not be the sole customer of these companies. So they will develop technologies in line with what NASA requires, but the companies will also be able to, open up the commercial sector. So I think NASA's comment, this is Thomas Zurbuchen, who's the head of Science Mission Directorate at NASA. He said NASA want to be the first customers, not the only customers. And that sort of sets the scene, really, for the big difference between this and what other, commercial companies have worked with NASA. Because, of course, commercial companies built the Saturn V rocket and its engines and all the rest of it. So, but in those days, NASA was the only client for these companies. Now the idea is that it will be a much broader remit. So just to give you the flavour for what's going on here, the 9 companies that have been selected are Astrobotic Technology Incorporated, Deep Space Systems, Draper, I don't know Draper, Firefly Aerospace Incorporated, Intuitive Machines LLC, Lockheed Martin.
That sounds interesting, doesn't it?
Yeah, great stuff. Marston Space Systems, Moon Express, and Orbit Beyond. These are, companies that clearly specialize in high-tech landers and things of that sort. So I think this is a great announcement and a big step forward. We're not there yet. NASA is planning, I think, to have humans walking on the moon again in the late 2020s. So we're still maybe a decade away. But it is thought that some of these companies might actually be sending their spacecraft to the moon within a year. The contracts that have been let not only concern building the apparatus, but getting it to the moon and getting the data back. That's all part of the deal.
It sounds like they're taking a little bit of an X Prize approach to it, because it does seem to me like they're wanting a bit of a competitive edge in this approach.
Yes, that's right. It's competition that's driving it.
Hello, Mandu.
He's chiming in there. Come on, Mandu. Oh, dear.
He wants to go to the moon.
The giant cat, he ought to be on the moon. The trouble is, if he went to the moon, it would shift the orbital balance of the moon.
Oh, dear.
Yeah, it might challenge the technologies to the limits.
I imagine.
Sorry, I've lost the thread of what
That's all right. We were just talking about the competition that's going into this process to get to the moon with a view to putting people on there in a decade. But this is also a preliminary approach to perhaps exploring Mars.
Yes, that's right. So the NASA definitely sees the moon as a stepping stone to Mars exploration. And I think it'll be another maybe 10 years after what we've mentioned already that it will. You mentioned the Lunar X Prize there, which I think was put up, I can't remember the exact figures, this is $30 million or something, to the first commercial company, non-government company that puts something on the moon. And that has never been claimed. I think that prize has been on offer for more than a decade. But nobody's managed to, develop the technology in order to do it, presumably on the budgets that are required. Whereas now, with NASA putting up this money to kickstart these companies, maybe the Lunar X Prize. I think actually the Lunar X Prize has now been withdrawn, so that they can't.
I think it had a deadline, and nobody reached the deadline. But when you look back at history at some of these great leaps in technology, these sorts of prizes were put up to achieve that. I think early flight was even part of this kind of process.
Maybe so. That's right. Yes, it's very likely.
Yeah.
Anyway, it's a good news story. It's altogether, I think there's $3.6 billion worth of contracts with this.
Wow. It's a lot of money, isn't it? I mean, when you think about it, splashing money around to sort of go and stand on another rock.
Yeah.
If you simplify it.
On the other hand, Andrew, as I always tell people, so that $3.6 billion is enough to keep the US military going for 31 hours.
Yeah.
That's my measure of,
That's a fair point. And when you put it in that perspective, people go, okay, that's interesting.
It is.
Yeah.
It's
so, and sort of it's a good argument for deflecting criticism towards astronomy as sucking up all this money that could go into, humanity projects.
Yeah. I mean, and that's also something I've said before, that it's never a straight choice. If it was a straight choice between exploring the solar system and doing humanitarian acts, then you would follow the humanitarian role. But it's not. It's a multifaceted thing, and governments spend money on this because they're investing in the future, basically.
Yeah. We'll have to get off this rock one day.
Indeed.
And we need the technology and the knowledge to do it. Exactly. All right. So exciting times ahead for NASA and those 9 companies. And yes, in about 10 years' time or thereabouts, we may see people pottering around on the moon yet again. You're listening to Space Nuts. Andrew Dunkley here with Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated number 1 by Tech Radar. This is the one I use. I've been using it for a couple of years and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy.
I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, yeah, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, Fred, still sort of talking about NASA projects. This one has actually made the news this week because it's reached its destination. We're talking about the OSIRIS-REx spacecraft, which I think is just the most awesome name. And it's basically arrived at a lump of rock too. But this is a targeted piece of rock known as Bennu.
Indeed, and this is really once again the kind of thing that we're seeing more of in our present regime of robotic exploration of the solar system. This is NASA's version. We've talked about Hayabusa, the Japanese version, also on these episodes, but. You're quite right that the OSIRIS-REx spacecraft, a NASA spacecraft which has been traveling since 2016, has just arrived in orbit around its target, which is an asteroid called Bennu. And as you said, off the top of your head, its name is 101955 Bennu, to give it its full asteroid
I'm amazed by my own memory.
So am I. So it's a big spacecraft, actually. I think it's, the size of a bus. It's not one of these miniature versions that we're seeing more of these days.
Yeah, I find that quite surprising. That's massive when you think about it.
It is.
Compare it to like Voyager or something.
Yeah, I should check its dimensions because I'm not too sure about that statement. I will check up on that. But it's an important mission. Because not only will this allow up-close and personal study of an asteroid, which is particularly interesting for a number of reasons, I'll get to them in a minute, but also the plan is that the spacecraft will actually return a sample of the dust of this asteroid back to Earth. So it's going to be another couple of years, maybe not quite a couple of years, something like 18 months, when the sample collection will take place. So the idea is to study the asteroid from orbiting around it, and at the moment it's only 7 kilometers. The spacecraft is only 7 kilometers above the surface of Bennu, so we're already seeing some great images. The asteroid will be photographed, will be imaged, will be analysed to death by remote sensing, but then mid-2020 we'll see this sample being collected from the surface, with a return actually about 3 years later, a return to Earth, because it's quite a long trip. The asteroid belt is between the orbits of Mars and Jupiter. Bennu is actually not within that main belt, but it orbits in a interesting way, because it's got just turning to the asteroid itself, it's a potentially hazardous asteroid. It's one that could collide with the Earth, so its orbit intersects the Earth's orbit, and in fact there is the statistics are that in something like 150 to 170 years down the track, late 22nd century, there is a non-zero chance of a collision between Bennu and the Earth.
Oh, you've got to love that terminology, a non-zero chance.
It's 1 in 2,700. So, that's it's pretty small, but it's not zero. And the thing about these collision statistics is that they're always based on probabilities, because you never quite know what what an asteroid is going to do. It could pass close to the Earth, and if this is in the meantime, one of its passes reasonably close to the Earth might well give it a little bit of a gravitational nudge that could change its trajectory enough that in 100 years or so that would bring about a collision. That's why it's all based on probabilities, because you can't be certain exactly where it's going to go. One of the other things that's of interest in this is, and it refers back to something we spoke about a couple of weeks ago, I think, and that's the Yarkovsky effect. This effect of the uneven heating of the surface of an asteroid, producing a thrust that actually accelerates the asteroid. So OSIRIS-REx, one of its tasks is going to be to measure that effect, and to give us an idea of how big it is. It's not really been properly quantified. I think I mentioned a couple of weeks ago that there was an experiment done some time ago that gave us some indication that the Yarkovsky effect is real and actually does change the orbit of asteroids. But this is a much more measured approach with a lot more detail being taken. And finally, the other thing that's really interesting about this asteroid is it's a particularly dark. It's dark in colour. It's got what's called a low albedo. It doesn't reflect that much of the sun's light. I can't remember what its albedo is, but it's quite low. And it looks as though...
Sounds like a few people I know. But anyway, go on.
This is... I'm not going to touch that. This is indicative that it's probably a rather primitive asteroid, but has a lot of organic compounds on its surface. You know, the materials that make up life, the carbon-containing chemicals that are of great interest to astrobiologists. And so the theory is that this asteroid represents a sample of the early material of the solar system, stuff that the solar system basically was formed from. And that's one reason why this asteroid has been chosen, to bring back a sample of this stuff and find out what's there.
And I suppose the other reason it was chosen is because it was reachable, because I imagine when you're sitting down going, okay, we're going to do this, and there are only a certain number of targets that would be feasible, I imagine.
That's right, yes, there are. And, you know, the other thing about any kind of exploration like this, you've got to wait for not the stars, but the planets to line up. You know, it's like when you're flying to Mars, you've got a window of opportunity to send a spacecraft to Mars, and then the next one is 2 years later or something like that. Because of the orbital mechanics of getting there. The same is true with Bennu. Bennu actually had, OSIRIS-REx actually had a slingshot with a planet called the Earth during its journey. So it was launched and then had another encounter with the Earth to give it a gravitational slingshot to get it out to Bennu with this two-year trajectory, more or less.
Yeah, well, with space travel, there is a lot of going backwards to go forwards, and I suppose we're witnessing that with the spacecraft that's trying to slow down to get close to the sun.
Yes, that's right.
It's going all over the place, but anyway, just to follow up on your wonderment at the size of OSIRIS-REx, I've found the dimensions, and with its solar panels deployed, it measures 6.2 metres in length, which is just over 20 feet.
Yeah.
It's about 8 feet wide, 2.4 metres. It's the same height, 8 feet, 2.4 metres, and it has a length of 11 feet when it's not got its solar panels deployed. So it's a pretty chunky piece of metal.
Yes, that's right, and it's going to do great things. Just to put a bit more detail on that, the OSIRIS-REx it's actually an acronym.
Oh, of course it is.
Origins, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. So it's got everything in there. The spacecraft carries every kind of instrument that you might expect with something that's remote sensing an asteroid. And its first task is just going to be to map the asteroid's surface. It's apparently doing 3 flybys over the poles of Bennu and its equator. That'll give an idea of its mass and its rate of spin and its shape, as well as detail on the surface to, just a few centimetres, tens of centimetres.
And for Australian cricket lovers, no, it wasn't named after Richie Bennu. Even though we think something astronomical should be named after Richie, this one wasn't. It's not even the same spelling. It's not even the same pronunciation. I'm really stretching here. But, I had to get a cricket reference in because the season starts this week. But yeah, I also heard, Fred, that it would have been there a couple of years ago, except that it took the committee that long to figure out what to call it.
That's probably true.
Yeah.
In some universe, anyway.
Yeah. We will watch with interest because some data will be coming back in the not too distant future from Osiris Rex. This is Space Nuts. Andrew Dunkley here. Fred Watson there.
3, 2, 1.
Space Nuts.
Okay, Fred, a couple of questions, and we say hello to Scott, who has sent us 50,001 questions, and we're going to do the one at this stage, but he promises more to come. He's got some real insight, as has Scott, when you read through all his questions. He's even got one there about flat Earth, or a flat universe, I mean. Flat Earth. That's been in the news a lot lately as well. But the question we're going to tackle for you today, Scott, is the one about the age of the universe. He says, the age of the universe, if the age of the universe is said to be calculated by reversing the expansion rate of the universe, how can this be calculated when we are told the expansion rate is not linear and is, in fact, in the early period, was an undetermined period of faster than light expansion? If this phase of expansion cannot be accurately determined, then the age of the universe cannot be determined accurately either? Question mark. So,
yeah, a great question, which goes to the heart of modern cosmology. Look, Scott is right. If all you've got is the expansion of the universe now, then your knowledge is a bit limited. But we know a lot more than that. So when the expanding universe was discovered back in 1929. You can actually plot something. You can derive from that something called the Hubble constant. In fact, we now, I think, where I'm right in. No, I beg your pardon. It's still called the Hubble constant. Okay. Hubble's law is now called the Hubble-Lemaitre law, because it was Georges Lemaitre, the Belgian priest, who said, well, if the universe is expanding, at some time in the past, it must have been all in a single point. And that really is the origin of the Big Bang theory back 1920s and 30s. And so, yes, if all you can see is the expansion of the universe today, and then you just linearly, interpolate backwards to say, this is how fast it's expanding now. If it's always been expanding at that rate, when would it have been zero? In other words, when would it have all been in one place? And actually, that gives you, with the present expansion, if you do that, you get an age for the universe of about 15 billion years, which is not that dissimilar from the age that we believe when you take into account the fact that, exactly as Scott has said, there has been a much variable rate of expansion over the history of the universe. So let's just step backwards. If you can look deep into space, say looking out to galaxies which are around 6 or 7 billion light years away, that means you're looking back 6 or 7 billion years. And in fact, what you're doing there is you're looking back to when the universe was half its present age. And you because it's about 13.8 billion years old, you can, by using particular techniques, and in fact the way this was originally done 20 years ago was by using supernovae, and it was the type 1 supernovae, which we're about to talk about as well. They act as standard candles. And so you can kind of chart, looking back all these billions of years, what the expansion of the universe was then. you can get a value of the Hubble constant that is not the Hubble constant today, but the Hubble constant back in the distant past. We don't quite do it that way. We actually have things called deceleration parameters and things of that sort. And until that was done 20 years ago, people believed that the expansion of the universe would have slowed down since the initial expansion because of the gravitational pull of everything in it.
That's what I grew up thinking, because that's what the common belief was.
It was.
Slow
indeed.
And then it'll come back and squash us all.
And it might come back and squash us, that's right. But back in 1998, by doing this measurement with the supernovae, it was realized that actually the expansion has increased in velocity. So we know that there is an accelerated expansion, and we can measure that. But there is one other ingredient that we have in all this, and this is really important when you're thinking about the very early universe, and that is, we can still see the flash of the Big Bang. We look back so far that we're seeing back to a time when the universe was still glowing brightly after the Big Bang. In fact, it's to a time about 380,000 years after the Big Bang. We call it the microwave background radiation because the stretching of the light waves by the expansion of the universe has turned it into microwaves. And so we can see that. And not only that, we can see a pattern imprinted on it of slightly higher and lower temperatures, very, very slightly. It's a very subtle pattern. But that is all about what are called baryonic acoustic oscillations. These are sound waves in the Big Bang plasma, the original, sort of mush of stuff that was still glowing brightly, had sound waves vibrating through it. And those sound waves imprinted themselves on the cosmic microwave background radiation. So we've got a kind of scale factor from that, because we know what these sound waves were about, and we know what they've turned into now, which is galaxies. And we can look at the way that it's like you might almost call it a standard ruler. We've had standard candles for the supernovae, but these baryonic acoustic oscillations provide a standard ruler. And it's that tells us kind of more about the early expansion of the universe, but also confirms the theory of inflation, which says that in the first something like 10 to the minus 35 of a second, the universe expanded very, very wildly by a factor of about 10 to the 50th. And Scott refers to this when he talks about the faster than light expansion, because indeed the universe was expanding faster than light. Of course, it can do that because it's only things moving through the universe that can't travel faster than the speed of light. So that is still a theoretical prediction, but all the measurements that have ever been made support the theory of inflation. There's really good evidence that the theory of inflation actually happened, this massive expansion immediately after the origin of the universe. Until
astronomers realised they've been using two different types of standard ruler and the ship falls over. Because that actually happened. That happened many, many moons ago, where two groups of people were building the same ship and they used different sized rulers and didn't know it until the ship was launched and it fell over.
Well, there's another version of that as well, with one of the NASA spacecraft that was using standard rulers in miles and kilometers when it came to orbit. That had an unhappy ending as well.
Very unhappy.
So that's a long story, but that's how we do it. It's not just the expansion today that we can measure. We can measure many other aspects of the expansion of the universe, which is how we determine the age of the universe. And as I said, I think it's 13.82 plus or minus 200 million years or something like that, the current rate of expansion.
Okay. Thank you, Scott. Hope that answered your question. We'll move straight on to the next one. This comes from Kevin Feel in Ireland. He said, "Hi guys, Kevin here from Waterford in Ireland." I knew that he was from Ireland. Started listening to your podcast a couple of weeks ago and now I can't drive to work without it. Gee, you must really be desperate. Anyway, I was wondering if you could answer a question I've been wondering about Type 1a supernova and how different stars with different temperatures could produce the same amount of light and energy every time. So that's the question. How is it so?
It's a great question, and it's got a fairly straightforward answer. So Type 1a supernovae are all formed by the same process, and that is you've got a star called a white dwarf star, and that's the ultimate fate of our sun. When the sun's gone through its red giant phase, what will be left will be this kind of glowing remnant called a white dwarf star, which has everything squashed together and only the pressure of the electrons holds it apart. It's called electron degeneracy. That's basically the technical term. So this white dwarf star, in a type 1 supernova, it's in a relationship with another star. So it's a binary system. You've got a normal star and a white dwarf star, and they're in orbit around one another, but they are so close that the normal star is feeding matter onto the white dwarf. The outer envelope of the normal star is kind of leaking off, and the gravitational pull is very intense of a white dwarf star. That's pulling it. That's basically pulling it into the white dwarf. Now, one of the things we know about white dwarf stars is that they have an upper limit to their mass, and it is 1.44 times the mass of the Sun. It's sometimes called the Chandrasekhar limit. So if you feed mass onto this thing and it exceeds 1.44 times the mass of the Sun, then you get this violent explosion, the supernova. And the supernova comes from the white dwarf exploding, and it's always a white dwarf of the same size because it's just triggered by this Chandrasekhar limit. So that's how we know that it's always the same amount of energy that goes into a type 1a supernova, because the white dwarf cannot be bigger than 1.44 solar masses. That's the mass that triggers the explosion, and that size basically standardizes the amount of light that comes from it. It's a great question from Kevin.
Brilliant.
And it's great to piece together the way astronomers do this, but that's how it works.
After that, Kevin, I'm never telling an Irish joke again.
I think you shouldn't either. I could have told you that at the start, but never mind.
Yeah. Well done, Kevin. That's fantastic. Thanks for the question. Thanks for everybody who sent questions this week, because when I mentioned in the last podcast that we hadn't had one for a week, we got about 1 million.
Yeah.
So we will work our way through them. We might have to dedicate another whole episode to questions very, very soon.
I think we will, yes.
And just one footnote to finish off. We also got an email from Peter Cox, who heard us talking about Elon Musk renaming his Falcon Heavy rocket. Sorry, Kevin. And he's called it Spaceship or something.
Starship, actually.
Starship. Yeah, well, it's just as bad.
It was the BFR, it's now Starship.
Yeah. And Peter's suggestion is we call it an Elon Musk stick. Now, Musk sticks are a sweet or a lolly that we have in Australia. They're about, 6 inches long, and they're very sweet pink thing made of, to taste like musk. And they were my favourite thing growing up, musk sticks. So I am fully behind you in renaming the Falcon Heavy rocket the Elon Musk stick. That is perfect, and he'll need to paint it pink. No doubt about it.
Quite so.
All right. Thank you, everybody, for your questions and your feedback and your input. We love it. And keep them coming. And thank you, Fred, as always. It's been a pleasure.
Always a pleasure, Andrew, and we'll talk again soon, I hope.
We will indeed. Fred Watson, astronomer at large. And thank you again, as always, for listening to Space Nuts. Catch you next time.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.